This is going to be one of the most important lectures of this course because every lecture after this one is going to build upon it. It might take more than the 50 minutes that is usually allocated to this lecture, so feel free to leave if you have to go to other courses, but it will be recorded and put on YouTube and also on Canvas. So you can come back and watch it later if you missed the last part of the lecture, but I'm just going to continue until I cover everything that I have to cover, because I want to have just one lecture that gives you all the basics of Ethereum programming. Okay, in the last session, we talked about the differences between smart contracts in Bitcoin and in Ethereum. Basically, in Bitcoin, the idea was that you have accounts, and every account has a public key and a private key that is known only to the owner of that account. And then you had this concept of coins, or unspent transaction outputs, sometimes called UTXO. And basically, you could take a coin and you could use it as the input to your transaction and send it somewhere else. And the inputs to each transaction had to be outputs of previous transactions, right? But then in the last session, we talked about Ethereum-like smart contracts. We said that we want to put code on the blockchain. And actually, this code is also some sort of an account, because our smart contracts or programs could receive money, right? So we said that we're going to change the accounting method. And instead of having this concept of unspent transaction outputs or unspent coins, we're just going to have a concept of balance. So every account is going to have a balance. And when I say every account, that includes the normal accounts that are owned by people, let's say, but also the contracts. And everyone on the network just keeps track of everyone's balance. So that's part of the consensus. And generally speaking, in Ethereum, we have two types of accounts. These are the words that we normally use. So we use the word contract account, of course, for smart contracts that are deployed on the blockchain. But for the other contracts, we usually use this kind of name. So we call them externally owned accounts. So externally owned accounts are basically accounts that are created using public and private keys, and basically whoever has the private key controls the account. Okay, sometimes I just call these normal accounts or people or so on. So basically, the most important thing is that we have two types of accounts. Now, every account can receive, hold, and send Ether and also other tokens. We don't really care about the other tokens in this course. We really care about Ether, which is like the base cryptocurrency on Ethereum. And every account can also interact with smart contracts. So every account can call functions in a smart contract. For example, if you are an externally owned account, you can create a transaction, as we've seen in the previous session, that calls a function of a smart contract, but also a smart contract can call a function of another smart contract. But a very important difference is in the way that these accounts are created, and also whether they can initiate transactions. So how do you create an externally owned account? An externally owned account is basically just a pair of public and private keys, right? So you just do key generation on your own machine. You generate new keys for yourself. This is just like in Bitcoin. And that's your account, right? Whereas a contract account needs a smart contract. It needs a code. It has to be first deployed on the blockchain. So the way a contract account is created is that some other account, let's say an externally owned account, creates a transaction that contains the code of this contract. And that transaction gets mined, it gets added to the blockchain. And when it's added to the blockchain, that creates the contract account. And from that point onwards, that contract can receive money, it can also send money and so on. And as we talked about this before, we basically just use hash pointers to refer to contract accounts. Okay. Now, the other really important difference is that externally owned accounts can start transactions. Okay, what does this mean? So I cannot have a situation where the contracts just create transactions on their own. Why? Because in that case, I might just have too many transactions. It might be hard to control them. There are all sorts of difficulties. So instead, I just say all the transactions have to start by externally owned accounts. So what can an externally owned account do in a transaction? These are the three things that we saw in the previous session. So if I'm an externally owned account, if I have basically the private key, I can create a transaction that either sends money to someone else, and I can send money to other externally owned accounts or to other contracts, or deploys a new contract, so it should contain the code of that contract, of course, or calls a function of a contract that was already deployed. But the really important points here are that, first of all, the transactions can only be initiated by externally owned accounts. And secondly, every transaction is signed by its initiator. So I cannot have a situation where I have a transaction, but I don't know who created it. In Bitcoin, this was possible. In Bitcoin, actually, you could create a transaction as long as it's valid. Maybe it doesn't even include any signatures. It depends on the transaction scripts, right? But here, it's not possible. Whenever you create a transaction, by default, you have to always also sign the transaction. So everyone on the network knows who created this transaction. And when I say who created this transaction, I mean the public key of the person who created the transaction, okay? So these are the important differences with Bitcoin. Now, there are some other small differences as well. I would put this link on Canvas. Please read this. You have to make sure that you understand all of these things. But the really important point, again, is that a contract cannot start a transaction. So every transaction starts by an externally owned account. But if I'm an externally owned account and I call some function in a contract, it's possible that that function then in turn calls another function in a different contract. That's allowed, okay? As long as the transaction is not initiated by the contract itself, it's fine. Okay. Anyway, I'm going to put these links on Canvas. Please read all of them in detail so that you can understand exactly how everything works. I'm just going to go to the next topic, which is the Ethereum virtual machine. So in the previous session, we said that there should be no ambiguity whatsoever about our programming language. So we should have a programming language, and then we should have a way of executing our programs such that we make sure everyone on the network gets the same result when they run the same code, right? This is actually quite hard to achieve. So one way to achieve this is to define a virtual machine, which is called the Ethereum virtual machine. And this is very much similar to the Java virtual machine, the JVM. And it basically defines exactly how a particular piece of code should be run. Again, just read this. It makes sure that everyone on the network basically has the same virtual machine and is running the programs in the exact same way. But now, how are we actually writing our programs? So what is the programming language that we're going to use? Now, here's the really important problem. The programming language is actually part of your protocol. So when you set down your programming language, you can never change it. Because if you want to change the programming language, you have to convince everyone on the network to switch to a new, different protocol, right? And maybe they don't. And if something like that happens, this is actually called the hard fork. So suppose that I propose I want to add this new type of operation to my programming language, and then half of the network agrees with me, and they just update their software and they say, okay, we're now going to support this new operation in the programming language. But then the other half of the network says, no, we're just going to follow the previous specification, the previous protocol. As soon as that happens, you have two different cryptocurrencies, because there are transactions that would be valid in one of them, but invalid in the other one, right? So it's really important that you design a programming language that never changes. But then, of course, this is not very desirable in the real world, because I might think of all sorts of new cool features for my programming language. Maybe I want to add something new to the language. So how do we actually solve this problem? And this is a problem that we've already had outside of blockchain in computing in general, and especially in the early days of computing. So you just define a low-level language, something like assembly, and then you can create high-level languages on top of it, as long as you have compilers that would translate from high-level languages to this low-level language that is actually used on the blockchain. So there is this paper that I would also want you to read. It's not too long, 25 pages. This is called the Ethereum beige paper, and it actually gives you all the important details of Ethereum, but it also has some tables at the end, and it includes a table of all the operations that are available on the EVM, on the Ethereum virtual machine. So these are called the EVM opcodes. These are the operations that you have. So for example, you have an operation called stop, which just halts the execution. You have addition of like two integers, you have multiplication, you have subtraction, integer division, so on. All of the normal things that you would expect a programming language to have. And you also have things like this. You have a hash function. Okay, so I have this low-level programming language, and it looks very much like assembly. If you've done any kind of assembly programming in your life, you know that the good thing about assembly is that you have very few operations. You can just define exactly what every operation does. So if you have a code written in this low-level language, there is a very well-defined semantics, and you can run it in exactly one way. So any code here will have just one possible execution, right? So everyone on the network can reach a consensus about the execution of this code. But of course, the problem is that this is not really human readable. No one wants to write code in this weird language. I mean, if you've written assembly code, you know how painful it is. So we're going to have a high-level programming language. Actually, in this course, we're going to use Solidity, but there are many high-level programming languages. And we're going to write our code in that language. And then there's a compiler that actually translates the code into this language, into the EVM bytecode format, as it's called. And then this bytecode format is what's actually deployed on the blockchain. So you actually wouldn't see this because all of this is automated under the hood. But at the end of the day, this is what goes on the blockchain. Okay, so all of the smart contracts that are deployed on the blockchain are deployed as bytecode. And by the way, whenever I say bytecode, I mean code in this low-level programming language. And if I want to talk about the code in the high-level programming language, I usually say source code. Okay, so we have this programming language, and it's great. We can write programs in it now. And we also talked about what the transactions can do and so on. But now we have to go back and look at one of the problems that we had with Bitcoin scripts. So remember, for the Bitcoin scripts, I said that one of the main limitations is the lack of any kind of loop operator. We didn't have a while loop, a for loop. We didn't have things like recursion and so on. But actually, this programming language here, the language that is used on Ethereum, is Turing complete, which means that you can write any program, basically, right? You can have loops. But then remember the problem that we were solving when we decided not to have loops in Bitcoin. The whole idea there was that if I can have loops, someone can write an infinite loop in one of the scripts, and then everyone on the network has to execute that script, and all the nodes on the network get stuck. I don't want that to happen. So now the question is, how do I actually avoid this here? And the answer that Ethereum has is a concept called gas. Now, gas is basically Ethereum's name for transaction fees. Now, if you go back to Bitcoin, remember that whenever you created a transaction, you could also decide how much you want to pay in transaction fees. Now, this was kind of an implicit decision in Bitcoin. You would just say that it's the sum of inputs minus the sum of outputs. But anyway, you had to pay a transaction fee, and you got to choose your transaction fee. Now, the idea in Ethereum is that you have to also pay a transaction fee, but this transaction fee is going to depend on the amount of computation that your transaction uses. So if you call, let's say, a function that has a while loop in it, and it does a lot of computation, then you would have to pay a lot of gas fee. You would have to pay a lot of transaction fee. And of course, just as in Bitcoin, the transaction fee is paid to the miner. Okay. Now, how does this work in practice? Well, this is how this works. If you look at this table, you have all of the opcodes in your low-level programming language in EVM bytecode, and you see that each one of these opcodes has a gas cost. So this means that if I run, for example, addition, if I want to add 2 integers, I have to pay 3 units of gas for that. If I do division, I have to pay 5 units of gas, and so on. Actually, there is an opcode that doesn't require any gas, and that's stop, because it just ends the execution, so you don't need to pay gas for that. But generally speaking, you see here that every operation has a particular gas cost. And like the hash function has a gas cost of 30 and so on. And some operations actually have huge gas costs. So for example, you have an operation called balance, which can ask for the balance of a given account. Remember, everyone on the network is keeping track of the balances of all the accounts. So you can also use this in your programming language. So in your program, you can actually access the balance of an account. But that's a very costly operation. It costs 400 units of gas. And there are many other things that you can see here as well. Again, just read this whole document. It's very eye-opening. Okay, now, suppose that I want to call a function. So I'm an externally owned account. I'm creating a transaction, and my transaction is calling a function in a smart contract. Basically, what's happening here is that I have to pay for the total gas usage of the execution that I caused. So 2 important points here. First of all, it's always the externally owned account that pays for gas. The contracts don't pay for gas, okay? Because the gas is always charged to the account that is initiating a transaction, and they have to pay for the entire gas of the transaction, which was actually my second point. And so the gas cost never comes from a contract account. It always comes from an externally owned account. Now, but how does this work actually in practice? Well, first of all, this whole table is part of the protocol. So everyone on the network has the same table. They will always get the same gas cost for every possible execution of code, okay? So again, this is part of the semantics of the programming language. So you would never have a case where 2 different nodes on the network disagree about how much gas a particular piece of code used. You will always have agreement on that. Okay. But the other thing is that this is like a gas amount, and its unit is just called gas units. But of course, when we were talking about Bitcoin, we could decide how much we want to pay in transaction fees. Here we can also decide, but we cannot decide an absolute value of how much we're going to pay. We can just decide how much we're going to pay per unit of gas. So actually, this is how things used to work. Now it's got a little bit more complicated. But I'm going to give you the old version, and then I'll tell you what the updates are. So the old version was that when you want to create a transaction, you can set 2 things. You can set the maximum gas usage of your transaction, and you can also set the gas price. So the amount of money that you're willing to pay for every unit of gas. So for example, I could create a transaction, and I could say that I'm going to pay for up to, let's say, 200,000 units of gas, and I'm willing to pay this much in Ether, let's say $5 for each unit of gas, okay? I'm not that rich, it's just an example. Now, what would actually happen? So everyone on the network, when your transaction gets added to the blockchain, of course, everyone on the network would start running the execution that you've asked for. So for example, if you were calling a function, everyone on the network sorry, would start calling that function and running all the commands in that function. But at the same time, they also keep track of the amount of gas that was used, okay? Now, if the maximum gas amount that you were willing to pay was more than the amount of gas that was actually used, you just pay for the gas that you used. So you would pay for the actual gas usage times the price that you were willing to pay for every unit of gas, okay? But suppose that I'm saying I'm willing to pay for at most 1,000 units of gas, and I want to call this function, and the function call actually uses more than 1,000 units of gas. What happens in that case? Well, in that case, everyone would just execute the function until 1,000 units of gas are used. And as soon as that happens, I run out of gas. And when I run out of gas, basically an exception happens. So this would revert the entire transaction. So everyone on the network would just know that this transaction is now effectively reverted. It's as if it never existed. So all of its side effects are reverted. If the transaction transferred some money around, those transactions are reverted. If it changed something in a smart contract, those changes are reverted, and so on. The only thing is that I lose my gas fees. So it's really important that you have a good approximation of how much gas your transaction is going to use. Because if you do not allocate enough gas, the only side effect is that you lose your gas money. So people will execute it, they see that there is not enough gas, they will revert all of the execution, and so there's no other side effect, but you lose the gas money that you had, okay? Now, this was how things used to work from the beginning of Ethereum. But then recently, in the last few years, they're changing how the gas prices are actually decided. So, and again, remember, the gas price is the amount of money that you're willing to pay for every unit of gas. Now, it used to be originally that you could just choose your own gas price. But now the gas price has two different components. There is a base fee, and then there is what we call a priority fee or a tip. So the base fee is chosen by the protocol, and it's like the minimum amount that you have to pay. You have no choice. You have to pay at least the base fee. And then the priority fee or the tip is chosen by you, and this is the extra amount that you're willing to pay. Now, there are several reasons for this. First of all, if you're creating transactions that are not really paying any fee at all, those transactions were just spamming the network and they wouldn't be picked up by the miners anyway. So to avoid the spam, they added a base fee to make sure you're paying at least some rational amount of money to create transactions. But then the other issue in Ethereum is with the creation of money. So remember that in Bitcoin, we said whenever a miner adds a new block, they get a block reward, and that's how new units of currency are created. It's the same in Ethereum. So you add a new block, you get to create some new units of currency. Now, the difference is that the block reward basically tends to zero in Bitcoin. It's going down every time. In Ethereum, they're continuing to give the block reward. So potentially there can be an infinite amount of Ether in the world over the years. Like every block is going to create new units of currency. Now, this is not an economics course, so we don't really care about economics, but basically the idea was that we want to also burn some money to make sure the total supply of Ether is not too high. So now when you have the base fee and the priority fee or the tip is actually paid to the miner, but the base fee is burned. So generally speaking, suppose that you're doing a function call, and this function call is using, let's say, G units of gas. So the amount of transaction fee that you would pay is G times base fee plus priority fee, okay? And then G times base fee is basically burnt. So those ethers are gone forever, and G times priority fee is paid to the miner. Okay. Now, the other reason for this concept of base fee is to make sure that you have blocks of roughly the desired size. So when we talk about block size, again, in Bitcoin, we had a fixed size for every block. We would say that a block has to be at most 1 million bytes. And we talked about this. We said that the whole reason for this is to make sure people have enough time to reach consensus. So if you had really huge blocks, maybe some of the nodes on the network could not keep up. But here, when you have a block, the block size in terms of like how many bytes of data is in the block is not really that important, because I can potentially have a function call that uses a lot of computation, but it's a very short function call, right? So I can have a block that is maybe 1 kilobyte, let's say, but it's using a lot of resources. It's causing a computation that is going to take a long time for all of the nodes on the network. So to make sure that's not going to happen, we're going to design our block size in a different way. So I'm going to say that the size of my block is the amount of gas that that block uses. And there is a hard limit, and the hard limit is 30 million. So every block in Ethereum can use at most 30 million units of gas. Now, there is, again, another economics part here where they want the blocks to, on average, use 15 million units of gas. And the way this works, the way this is incentivized, is that if a block uses more than 15 million units of gas, then the fee increases, the base fee increases for the next block, okay? But if a block uses less than 15 million, then the base fee decreases. So the idea is that you're also creating a balance between supply and demand. Again, not an economics course. You can read this, you can see how the base fee works. In our case, at least in this course, all we really care about is the total gas fee, which is like base fee plus tip. But we have to also always be careful that the maximum amount of gas that can be used in any block is 30 million. Again, this is so that everyone on the network can catch up, so that we make sure everyone can execute all of the transactions in a new block and they can reach consensus about the what we call state of the world. And state of the world is basically the balance of every account and also the state of every contract. Like all of that is called the state of the world. And of course, we want to have consensus about the state of the world. But if every block can do many operations, then some of the nodes on the network cannot catch up. So we make sure that every block can do at most, and can spend at most 30 million units of gas. Okay. Now, the other point I have to tell you is that you pay gas not only for execution, but also for storage. So whenever you're creating a transaction, that transaction is going to be put on the blockchain, right? And we said that every node has to keep track of the blockchain. So every node has to store your transaction. So you have to also pay some money for that storage. Similarly, when you have a smart contract, maybe that smart contract has a bunch of variables. And we said that everyone on the network has to keep track of the state of every smart contract, so all the variables of the smart contract. And let's say I have a smart contract that has an array, and I keep making this array bigger and bigger, right? Every time I'm using more storage, I'm actually requiring everyone on the network to keep track of it, so I have to pay some gas for that. So the gas costs are not just for operations that do some calculation, but there are actually gas costs for storage as well. Again, read this document, you will see the exact gas cost for everything. Okay. Now, and of course, this reaches our main goal, like our initial goal, which was to make sure that no one can spam the network, no one can do a denial of service attack. Because imagine that you want to force the entire network to do a lot of calculations. First of all, the most extreme case, suppose that you write a piece of code that has an infinite loop. And then you call that function, which basically has an infinite loop. It's not going to work, right? Because you have to pay some gas. So you have to set a gas limit. You have to say how many units of gas you're going to use. And the gas limit is at most 30 million. So you cannot use more than 30 million units of gas anyway. And then you also have to pay for all the gas that you're using. So, well, it doesn't really make sense to do this kind of attack. You will just bankrupt yourself. Like, people will execute the code until at most the amount of gas that you have allocated to it, and you have to pay for it. So if you have a piece of code that needs more than that amount of gas, it's basically not executable. You can just waste your gas money, but nothing happens to the network. By the way, this is a really important point. We will see a bunch of attacks based on this. So when people forget that there is a limit on the amount of gas that they can use, it's actually possible to write contracts that have functions that can never be called, right? Okay. So with all of this being said, let me finally go to Solidity. So Solidity is a high-level programming language. And this is how we actually write contracts, at least in this course. There are other high-level programming languages as well. But again, remember that there is a compiler, and the compiler basically compiles this high-level code to this kind of code. And this bytecode is actually what's deployed on the blockchain. So people on the blockchain only see the bytecode, but of course you're developing the source code. Now, we're going to use Remix here. Remix is an online IDE that was actually created by the Ethereum Foundation. You can also use whatever IDE you like. There are plugins for Solidity in all of the commonly used IDEs. But I like Remix. It also has like a compiler here. And it also has a virtual machine, which basically virtualizes a blockchain. So this is just for development. It's not working with an actual blockchain. It just has a simulator, so I can simulate what happens with my contracts. Now, during this course, we will sometimes see that this simulation is not great. Like, there are things that can happen on the real world blockchain that don't really happen in this simulated environment. But we will talk about that when we get there. And you can see that there are some example contracts already there, so you can look into them. Today, we're going to just write some very basic contracts. So let me create a new file. I'm going to call this one basic.sol. And SOL is the file type for Solidity contracts. Now, generally speaking, you can look at the examples to figure out how you can write Solidity code. But let me give you some of the important things here. So first of all, whenever you're writing Solidity code, you have to make sure you start by telling what version of Solidity you want to use. So I can put something like this at the beginning of my code. And basically what this means is that for this particular smart contract, you can use Solidity compilers with these versions. So more than this version number and less than this version number. You can also set a particular version number. You can say, I want this to be compiled only with this version number, okay? But the important point here is that you have to always do this because the language changes, the high-level language changes, and you will have newer version of the compiler. And even if the language doesn't change, maybe the compiler changes, because maybe the compiler just has some updates. Maybe there are new optimizations, better ways of translating from source code to bytecode and so on. But you want to make sure that your contract is always compiled with the same version of compiler that you were using when you wrote the contract, because otherwise you might have some sort of behavior which was not anticipated by the original programmer of the contract. So it's really important that we have this. And again, as usual, I have a Solidity compiler here. It does compilation automatically. I don't have compiler errors here. There are just a bunch of warnings. Okay, so let's say I want to create a contract. Now, a contract is pretty much similar to a class in Java. The only difference is that instead of using the keyword class, I'm going to use the keyword contract. So I'm going to create a contract, and I'm going to call it basic contract. Okay, so this is my contract. Now, in this contract, I can have a bunch of variables, and we call these storage variables. So for example, I can have an unsigned integer called x. Okay, now here's the thing. These variables are basically kept by every node on the network. So when I have a variable like this, which is outside of all the functions, and I call this a storage variable, every node on the network keeps track of x and keeps track of what the value of x is, because the value of x might change based on some function calls in this contract. So actually creating this kind of variable is pretty expensive in terms of gas, because everyone has to keep track of it. So if I have a contract like this and I deploy it, I will have to pay for the gas usage of this storage or memory that I'm using here. Okay. But anyway, I can create variables. There are many different variable types. So uint is unsigned integer. There are maps. There are strings. You can Google this and you can basically see how to code in Solidity. I would just say that by default, the variables in Solidity are 256 bits. So when you write uint, that's basically a 256-bit variable, but you can also create a 64-bit variable or a 32-bit variable or so on. So you have all of those data types. Okay. And also all the variables are initialized to 0. Again, remember that when we're writing smart contracts, everyone should agree about the state of the smart contract. So we cannot have any kind of undefined behavior. So there should be a standard on what the default value of the variables are. And the standard is that they're just 0. Okay. Now I can write a bunch of functions here. So let's say I want to do the simplest thing. Let's say I just want to have two functions. One of them sets the value of x, and the other one just returns the value of x. So let's say I have a function called set, and this function is going to take some integer y, and all it's going to do is that it sets x to be equal to y. Okay. Now, you would already see that I have a compiler error here, and this is the error that it says. It says that for this particular function, you have not set any visibility. So whenever I create a function, I have to set the visibility. So I can say, for example, this is a public function, or I can say it's a private function. Okay, there are also other levels of visibility. You have internal and so on. Now, what does this mean? First of all, it's kind of a misnomer. So if you say this function is private, it doesn't actually mean that other people cannot see it. Because at the end of the day, you're compiling this contract, and the compiled version is going to be put into a transaction, and it's going to be put on the blockchain. Now, the blockchain is public knowledge. Everyone can see the blockchain. So everyone can see every contract that is on the blockchain. So if you write private here, it doesn't mean that other people cannot see the function set. Everyone can see it. The only thing here is about who can call this function. So if I say that this function is public, it means that any account can call this function. And remember, again, we have two different types of accounts. We have externally owned accounts and contract accounts. So an externally owned account can create a transaction which basically calls the function set and gives a value for y, right? That's what it means when I say this function is public. But it also means that other contracts can call the function set. So maybe an externally owned account calls some other contract, and then in its code, that contract calls my contract set function. That's also possible. But if you set this to private, then this function can only be called within your own contract. Okay, so other contracts and other externally owned accounts cannot call it. Again, it's called visibility, but it's not really visibility. Everyone can see this function. Okay. So I just set this to public. So I say that anyone can call the function set, give a value y, and that would change the value of x to y. Now I can also have another function. Let's call this one get. And this one is also public. And I say that it returns an unsigned integer, and it just returns x. Okay. Now, this is my very simple contract, the simplest possible contract I could think of. Now, I have this contract. It's also compiled. Again, I've put the compilation on automatic, so it automatically compiles everything. So now I have the bytecode of my contract because I've compiled it. Now that I have the bytecode, I can actually create a transaction that contains this bytecode and puts the bytecode on the blockchain, right? And to do that, I can just go here. Again, this is a virtual machine, as you see. There are also all sorts of other virtual machines or test nets that you can choose. But in this course, we're just going to use the Remix virtual machine. So in this virtual machine, it already gives you a bunch of accounts. And remember that accounts are basically, and these are externally owned accounts, so they have a public key. This is their public key, and they also have a private key. But for testing purposes in this virtual machine, you can basically create transactions using whatever account you want. And when you're creating a transaction, you can set a gas limit. So this is, as we talked about before, the maximum amount of gas that the transaction is allowed to use. And if you don't allocate enough gas, your transaction will, of course, run out of gas and it will be reverted. But one thing I have to tell you is that this virtual machine actually has a bug, and sometimes it does not enforce the gas limit. So be careful, the gas limit is actually enforced on the actual blockchain, even if it's not enforced here. Okay, so I can choose an account. Let's say I choose this first account. I have set the gas limit for my transaction to 3 million, which is the default value. And I say, deploy this contract, basic contract. Okay, so I'm going to put the log here and let's call deploy. Now, this was a successful transaction. So this contract was deployed. Again, in the real world, this would not be instantaneous. You have to wait for the transaction to be picked up by a miner and added to the blockchain and all of those things. But here it's just a simulation, so your transaction got added to the blockchain instantly. Now let's see what happens here. If I look at this log, if I open the log, it says that, well, the transaction was mined and the execution was successful. This is the transaction hash. This is the block hash. It was added in block number 1. Of course, this is a very weird block number because, again, we are in a simulation, so we're just at the beginning of our blockchain in some sense. Now, the contract has an address. You see, and again, we've talked about this before. You can point to contracts by their addresses, and this is basically a hash pointer. So whenever I want to interact with my contract now, I can just use its address. Okay, but this transaction was created by this account, by the account that ended in C4, and so it was also signed by this account. You can also see how much gas it used. So this is the amount of gas that it used, and there is a transaction cost. This is the cost that you're paying, the amount of gas that you're paying for all the nodes to just keep track of the transaction, to add the transaction to their copy of the blockchain. And then there is an execution cost, which is like the rest of the gas that you're paying. And here you can see that I have this basic contract. This is the address of the basic contract, and I can now actually interact with it. Okay. So let's do this. And by the way, as you see, the contract also has a balance, and the balance of the contract is 0. And another interesting thing is that the balance of this account changed. Why did the balance of this account change? Because this account had to pay for the transaction fee. So that small amount that was taken from here is actually the transaction fee that we paid. Okay. Nice. Now, let's continue with this. I can call the function get, or I can call the function set. Again, anyone on the blockchain can do this, so I can maybe switch to a different account. I switch to this second account, and I call the function get. Now, here's the thing. If you look here, this is also creating a transaction. So there was a new transaction created. It was added to the blockchain, mined, it's in block number 2, and it uses gas. So calling a function is also a transaction that causes you to pay for gas. And as you see here, this account paid for gas, and now its balance is less than 100 Ether, which was the original balance. Of course, we're working with fake money here. This is just a virtual machine. But you can also see the output. So you can see that the function get returned a value of 0, which is of type U in 256. Okay. Now I can also use set, but set is a function that needs a parameter. So I can give the parameter here. Let's say I set 100. So I do this. Again, this is a function call. I paid for gas and everything. And now the value of X is 100. But very importantly, I said that everyone on the network keeps track of the value of X. So this is subject to consensus, and everyone on the network now knows that the value of X is 100. Okay. Now, if I do get again with maybe another different account, you see that it now returns 100. Okay. And again, all of these are transactions, and all of them use gas. Nice. Let's go back here. I can also make my variables public. And if I write public here, again, it doesn't mean that it was private before, because everyone on the network was keeping track of the value of X anyway. It just means that the other contracts can now also access the value of X. And if I deploy this new version of my contract, you would see here that I can now also ask for the value of X. And it gives me 0. Anyway, so these are some of the basic things that we could do. But of course, we are interested in paying money to the contract and in also being able to take money out of the contract. So here's how I can do that. I can create a function that is payable, which means that you can actually pay the contract at the same time as calling that function. So I'm going to create a function. Let's call this function, pay contract. And I say that this is a payable function. Okay. Now in this function, for now, I'm not really going to do anything. So it's just a function that can take money. And of course, I have to also say if it's public or not. So I say it's public. Anyone can call this function. So now this means that anyone can call this function and give money to the contract. So first, I'm going to deploy my contract. And by the way, every time that you deploy a contract, it can never be changed from that time forward. So the contracts that are deployed on the blockchain, they're immutable. You cannot change the code of a contract after you deploy it. Be very careful about that. I'm changing the code and deploying again and so on, but from the point of view of the blockchain, every time that I'm deploying, I'm creating a new contract. And this new contract is completely different from the previous contract. So you can never change the code of your contract after you've put it on the blockchain, which is actually a very good reason for making sure you don't have any bugs or security vulnerabilities. Because if you do have bugs, there's no way to fix them. Your only chance to find all of the bugs and security vulnerabilities is before you put your contract on the blockchain. Okay. So let's go here. Let's deploy this new version of the contract. And by the way, when I remove some contract here, it's not actually removed from the blockchain. It's just removed from my view because, again, the blockchain is immutable. When you put something on the blockchain, it's there forever. Okay. Now I've deployed my contract. Now I can go to a different account. Let's say I want to use this account now. And now let's say I want to call this function, this payable function, which was called pay contract. I can also decide how much I want to pay. So I have 100 Ether. Let's say that I want to pay 8 Ether to this contract. By the way, here you see several different units of money. You can see in the beige paper what they actually mean. So it's like the smallest unit of money is Vey, and then you have Shabo, Fini, Ether, whatever. And like 1 Ether is, I think, 10 to the power of 18 Vey. So whenever you're writing code and you're working with money, the unit is always the smallest unit. It's always Vey. So 1 Ether would correspond to 10 to the power of 18. But anyway, I'm going to go back here. I've deployed this contract, and now I'm using this account, which currently has 100 Ether, to pay 8 Ether to this contract. So I set the value to 8 Ether, and I call the function payContract. Again, this function call was successful. It was mined, it was added to the blockchain, and so on. Here's the differences from the previous cases. So as you see here, the balance of my contract is now 8 Ether. Okay. So now the 8 Ethers belong to the contract. And if you look at the balance of the account that I used, it went down by 8 Ether, but it also went down by a tiny bit for the gas fees that I was paying. So I'm always paying gas fees for all of the transactions, and this includes the current transaction. So actually the total cost was a little bit more than 8 Ether. But this is one of the worst things that you can do in a real world contract, because this money is now stuck. So this money belongs to this contract, but if you look at the code of my contract, there is no way to get this money back. I don't have any function in this contract that actually pays the money back. So this money is effectively burned. This money is under the control of the contract, and the contract is never giving it back. And well, of course, the code of the contract is immutable. You cannot change the code of the contract, so that money is gone. You're not going to get that money. You can change this contract and deploy a newer version that actually fixes this, but then the newer version would be a different contract at a different address. And so this money belongs to the old version at this address, and you cannot change the code of the old version, so this money is just gone. Of course, this is, again, fake money. This is a virtual setting, so I didn't actually waste this much, but it has happened a lot in the real world that people just pay money to the contracts, and it gets stuck in the contracts, and they cannot get it back. Okay, so how do I get money back from the contract? First, let me tell you about the data type that exists in Solidity, which might be a little bit weird for you because it's not normal and it doesn't really exist in other programming languages, and that's address. So I can have a variable of type address. Let's call it owner, for example. Suppose that I want this contract to have an owner, and I want to have a pointer to the owner of the contract. I can use address. And basically, the address is the address of the account. So, for example, I can say that this account is the owner. So I can just copy the account address, and I can say the owner is this. Okay. But contracts also have addresses. So for example, if I deploy this, you see that this contract also has an address. This is the address of the contract. And I can also copy the address of the contract. And I can say that, so this variable owner is actually containing the address of some other contract. Okay. So basically, an address is a pointer to another account. And again, as before, we have two types of accounts, and we can point to both types. We can point to both externally owned accounts and contract accounts. Okay, for now, let me say that I want to have the owner be this account, the account that ends in 72. Okay, so again, this is just a variable, and address is the variable type. So I have an address of the owner. I'm saying that this is the owner of this contract. Let's say I want to create a very simple contract where everyone can pay the contract, but only the owner can take money out of the contract, okay? So I'm going to remove all the things that we didn't need. I don't need set and get anymore. I have a function called pay contract that pays it. And let's say I have another function called take money, which takes money from the contract. So I say this is public. Now, here's what I'm going to do. I want to talk about the person or the account who has called this particular function. And I can access that by writing msg.sender. So msg.sender is whoever calls this function. It can be an externally owned account. For example, maybe I'm calling take money in a new transaction, and then I would be msg.sender. But it can also be another contract, because maybe I'm an externally owned account, I'm calling some other contract, and then that contract is calling the take money function here. So msg.sender would be that other contract. Okay. Anyway, I want to say transfer the money that this contract has to msg.sender. Okay. So msg.sender is an example of a global variable. These are the things that you can actually access in your contract. So you can see here, for example, there is msg.sender, which is the address of the account that sends the current transaction or called the current function. There is msg.value, which is basically the amount of money that is attached to this transaction, to this function call. There is block.coinbase. This is the address of the miner who mined the current block. You have difficulty, gas limit, block number, block timestamp. One important point is that you have something called tx.origin that you can use. Now, there is a difference between msg.sender and tx.origin. So tx.origin is the original externally owned account who created the current transaction. But msg.sender is the account that called the current function. So if I'm just calling this function as an externally owned account, if I'm just calling take money using my own personal account, I would be both msg.sender and tx.origin. So, and of course, the type of msg.sender and tx.origin is address. But if I have another contract and I call that contract, and then that contract calls take money in this contract, then msg.sender would be that contract. It would be the account that called take money. But tx.origin would be my externally owned account, the account that started the chain of execution. Okay, so there is a difference between tx.origin and msg.sender, and tx.origin is always guaranteed to be an externally owned account. And also the other thing is that you can actually trust these values. Why can you trust these values? Why can you be sure that tx.origin is really giving you the externally owned account that was the origin of the current function call? That's because we said that every transaction is signed. So whenever I'm creating a transaction as the origin, as the externally owned account, I have to sign it. So you don't have any fake transactions. You can make sure that this transaction was actually created by tx.origin. Okay? And all of these signatures are basically checked by default. They're all validated. And if a transaction doesn't have a valid signature, of course, it's an invalid transaction. But anyway, in my function, I can write msg.sender to refer to the person who should receive this money. So I'm going to say, let's create an address. I'm going to call it recipient. And I'm going to say recipient is just msg.sender. Okay. Now, how much money do I want to send to this recipient? Let's say I want to say recipient.transfer, and I have to write the amount of money in VEI. So I'm just going to put some number. So I'm going to say send this much money to the recipient. Okay. And again, remember my unit is VEI. Now, if I want to do it in Ether, I could just write something like this, 1 Ether. Okay. This. I'm not sure if you need the multiplication or not. Anyway, you can do 10 to the power of 18, and that's 1 Ether. But anyway, let's say I'm sending this much money. Now you see again a compiler here, and this is a very interesting compiler. So it says that transfer is only available for objects of type address payable, not address. So this is a check that is built into the Solidity language to make sure that you don't pay someone by mistake. So when you have an address, you can actually have two different data types. And one data type is just called address. The other data type is called address payable. And you can pay someone, you can pay an address only if it's payable. So this is just a distinction in the high-level Solidity programming language to make sure you don't pay anyone by mistake, to make sure that if you're paying someone, you actually meant to pay them. So for example, if I know that in this contract, I'm going to pay the owner, I would say that owner is an address payable, right? But the other thing is that you cannot just convert between addresses and address payables automatically, because that would potentially also create bugs. Maybe you would again pay someone that you didn't intend to pay. So you see here, there's a compiler error that says address is not implicitly convertible to address payable. So you have to be explicit about it. If you want to make something payable, you have to always say, I know what I'm doing and I'm making this payable. I know that I want to send money to this address. And then it wouldn't give you a compiler. So here it's the same thing. msg.sender is an address. I say I'm intentionally making it payable because I want to send money to this address. So I have this recipient, and then I say recipient.transfer this much. Okay, let's deploy it. Again, this is still kind of a stupid thing. So I deploy this contract, and this is my contract. Let's say I pay it some money. I pay it 10 Ether. Okay, now the balance of the contract is 10 Ether. But look at this. This function take money is public. So anyone can call this function, and this function actually pays you. So anyone on the network, for example, this one, this account, can come and just call take money. And as you see, this was a successful transaction. It was mined and added on the blockchain. So it took some money from my contract, and actually it gave the money to this account. I mean, it was a small amount. And actually, the amount that it received is not exactly the same amount as here, because, of course, it had to also pay for transaction fees. But anyway, this is a really stupid contract that allows anyone to take money out of it. And if I'm an attacker, I would just keep calling take money and take money out of this contract, right? So again, don't write these kinds of things. I'm writing it in this virtual machine because it's fake money, but with real money, you shouldn't do this kind of thing. Okay. So what do I want to do? I want to make sure that only the owner can take the money. So I say recipient is this, and I say only if the recipient is the owner, transfer the money. Okay, but also I don't want to just transfer a small amount of money. I want to transfer all the money in the current contract. So how can I get all the money in the current contract? Well, it's just like in Java or C++. You can refer to the current contract by the keyword this. Now, I can take this and I can first convert it to an address, and then I can use the keyword balance to get the balance of this address. So remember, every address, every contract has a balance. And well, I mean, every account has a balance, be it a contract or an externally owned account. So everyone on the network is keeping track of the balances of all addresses. And all I'm saying is that the amount that I want to transfer is the entire balance of the current contract. Okay? So now let's say I deploy this contract, and let's say I pay it 5 Ether. Okay. So now here you can see that I have the contract, and this was the previous version. Oops, what's going on here? Okay, I don't know what's happening. Let me do this again. So I deploy the contract, and I pay it 5 Ether. Okay, so my contract now has 5 Ether. Now, I'm going to try to take money from it. So let's say I use this account, the account that ends with 4C, to take money. Now, as you see, the balance of the contract did not change because this account was not the owner, so this if failed, and the contract did not pay out any money. So the only result is that this account now has less money because it paid for gas money. Okay. But if I choose the actual owner, so the owner is the account that ends in 72. So this one is the owner. The owner can call take money. And when the owner does this, you see that the balance of the contract became 0, and the balance of the owner went up by the balance of the contract, which was 5 Ether. Again, minus the transaction fees, minus the gas fees. So this is how you can take money out of a contract. This is now a very simple contract in which anyone can pay, but only the owner can take the money out. Okay. Now, another thing that I want to tell you is that you can also write a constructor function for your contracts, and this is just called constructor. And all it does is that it's called the first time the contract is deployed. So remember, you can have a transaction that deploys a contract. But when you deploy the contract, it also automatically calls the constructor function so that it can initialize some things. So for example, maybe I have this owner, but I don't want to hard code it. I want to say the owner is whoever deploys the contract to the blockchain. So in my constructor, I would just say owner is tx.origin. Or I could also use msg.sender, whoever is deploying this. Now, again, I have an error here because owner was payable and tx.origin is not payable. So I have to be careful to make it payable explicitly. Okay. And as you see here, it now works. Okay. Another example that I can give you is using requirements. So remember, I told you that if a function call runs out of gas, it will basically just be reverted. And I said that by reverted, I mean that everyone on the network just assumes that this function call or this transaction did not exist in the first place. So any side effects of this transaction will be reverted. The only thing that will not be reverted is the amount of gas that you paid for it. Okay. So let me see if I can do something like this. So it might not work in the virtual machine, but it will work in general. So let's say I have a function called infinite loop, and it's a public function. And all it does is an infinite loop. So I have, let's say, a while loop, and it says while 1 is greater than 0. So an infinite loop, do something here. I don't know. Say x is, I don't know, let's just have some u and x here, and just say x equals 1. Okay. I'm not doing anything. I just want to have an infinite loop. I could also leave it empty. Now, you see that there is a warning here. This warning, we will talk about it later. Basically, what it says is that you can make this function pure. Now, a function is pure if it's not changing anything in the contract. Okay. But we will come back to this. And actually, sorry, I have to probably tell you about these two things. Okay, so when you are creating the functions, you can also have some extra keywords. For example, if I have a function that is only reading from the contract, for example, let's say I have a function called getOwner, and it returns an address, okay? And I just say return owner, okay? Now, again, I haven't set any visibility. Let's say this is a public function. Now, here's the thing. This function is not really writing to anything in this contract. It's just reading from the contract, right? So it says that I can change it to view. So I can just write view here, okay? What does this mean? When I write view, the keyword means that this function does not change anything in this contract. It only takes some information from the contract. So if I want to call this function, I don't actually need to create a transaction that includes this function and then have it mined on the blockchain and pay for gas fees and all of those things. I can just run this function on my own machine, right? Because on my own machine, as a node of the blockchain, I know exactly what the current status of the blockchain is. So I already know what the owner is. I can just run this function on my own machine. I don't have to pay a miner. I don't have to pay transaction fees. That's what it means for this function to be view. And actually, there is a special kind of view, which is called pure. I can say that this function is pure. And a pure function is a function that doesn't even read from the blockchain. So as you see here, it's just like a normal function. It's not doing anything with the blockchain. It's not writing anything. It's not reading anything. So I can just make it pure. And again, just like a view function, if I have a pure function, I can just run this function on my own machine. I don't need to put this function in a transaction and have it mined and pay for transaction fees. Okay, so that's what pure and view means. But I want to write a different type of function here. So let's say that it's a function that has an infinite loop. And in this infinite loop, it just sets owner to be msg.sender. Okay, I have to also write payable as usual. Okay, so this is an infinite loop. And of course, I hate infinite loops because they will run out of gas. Now, I don't know if this virtual machine does the gas calculations correctly. But anyway, let's deploy this contract. I have deployed it. And you see here that my gas limit is 3 million. I'm going to call the infinite loop function. And I called the infinite loop function. It says the transaction is pending. It's basically simulating everything. It's going to run out of gas, and it's going to give me an error, hopefully. Unless, okay, this is bad. No, it's just trying to run it. The virtual machine got stuck. Okay, in the real world, if you do this, you will run out of gas. So you would have paid for your gas money, but the execution cannot succeed. Now, when the execution cannot succeed, everything that was done in that execution is reverted. So the owner doesn't actually change, right? Because the owner was changed by this execution, but it didn't succeed. It got into an out of gas exception, again, in the real world, not in this virtual machine. And when it gets into an out of gas exception, the whole thing is reverted. Okay, let me see. I have to probably refresh this. Yeah, okay. These kinds of things happen all the time with this virtual machine that we have here. Anyway, so that's what happens if you have an infinite loop. But I can also create exceptions myself. So for example, in this take money function, I wanted to say that only the owner can take the money, and I did this with an if. But instead of this, I could just have something like this. I could just say, this is a function that pays the owner. So owner.transfer balance of the current contract, right? So no matter who calls this function, it will always pay the owner. But of course, I wouldn't be happy about this because maybe I'm the owner and someone else calls this function, and maybe I didn't want this function to be called. Maybe I wanted my money to remain in the contract. So I can write here, I can write require that msg.sender is the owner. Okay. And so this is a requirement, which means that this function will successfully execute only if this requirement is satisfied. Now, what happens if this requirement is not satisfied? Basically, the same thing that would happen if you run out of gas. It's an exception, which means that the entire transaction gets reverted. Okay? And if the entire transaction gets reverted, then all of its side effects are reverted. The only side effect is that the person who made that transaction is paying for gas. So let me deploy this. So I have this contract. I can ask who's the owner. The owner is the account that ends in C4. And let's say the owner wants to pay 5 Ether to the contract. So now the contract has 5 Ether. And now let's say that someone else comes and tries to take the money. Okay, so as you see here, this transaction was not successful. It says the transaction has been reverted. Now, when it's reverted, again, the balances remain the same. The only change is that this current account doesn't have 100 Ether anymore because it paid for the gas. But also any other change by this function would be reverted. So suppose that I had some integer x here. Let's say I have x, and originally I say x is 5, and let's say this x is also public, so the constructor sets x to 5, and let's say whenever you do take money, it first sets x to 2, okay, something like this. So let me deploy this contract. So I deploy it. I can ask who's the owner, and as you see, the owner is the account that ends with B2. So let's say I pay 10 Ether to this contract. All of these are transactions. And I can look at the value of x. The value of x is 5, which was the original value. And now let's say someone else other than the owner tries to take the money. So this means that they're creating a transaction that contains a call to take money, and this transaction is added to the blockchain. So I do this, and as you see, it failed, and it got reverted. So what's happening here? This account is calling take money. So the execution of take money starts, it sets x to 2, and then it checks this requirement. But the requirement is not satisfied, so the execution stops, but all of the changes are reverted. So this change of the value of x is also reverted. Everything that was done by the current transaction, by the current function call, is reverted. So now if I ask for the value of x, I should still get the original value, which was 5. And as you see, the value of x is 5. But if the actual owner, which was this one, right, comes and calls take money, you see that it succeeds, the transaction succeeds because this require was successful. And so this transaction is not reverted now. So the value of x is now 2. If I ask for the value of x, as you see, it's 2. Okay. Now, finally, I want to do one last thing today. And this last thing is to show you kind of a very silly Ethereum smart contract, which is called King of the Ether. Now, this is a real contract, and as you see, people were actually using it, so you can look at this webpage for more information about it, but we're going to just write a simplified version of it. Now, the basic idea is that it's a Ponzi scheme. So you get to pay this contract to declare you as the king of Ether, whatever that means. Okay, so I'm going to create a new contract here. Let me do this. I'm going to call it King of Ether. SOL. And so I have to start by saying what is the version of Solidity that I'm using. And I'm going to create a contract. Let's call it King of Ether Throne. This is my contract. Okay. And I'm just going to have an address in my contract, which is called king. So you get to pay to become king. And I'm going to have a constructor which simply sets the king to whoever deployed this contract. So king is msg.sender here. Again, you have to be very careful about the type casting. So I'm casting the type to payable so that I don't get an error here. Okay. And then anyone can pay to become king. And you would become king if you're paying more than the previous king, if you're wasting a lot of money, basically. So the whole point of this contract is to show that you're rich. And when you become king, the money that you paid would actually be transferred to the previous king. So I'm going to also have a price this is the price that you have to pay to become king, and originally the price is 0. I didn't have to write this because that's default behavior anyway. And let's say I just have one function, which is called depose. So you depose the previous king and you become king. And it's a public function and it's payable. Now, in order to be able to depose the previous king, the amount of money that you're paying should be more than the price. So I'm going to require that the amount of money attached to this function is more than the price. Now I can get the amount of money attached to this function by writing msg.value. So msg.value should be bigger than price. Otherwise, it will just revert. Okay. And then I'm going to say if the value that was paid was actually bigger, then the king becomes whoever sent this message. King becomes msg.sender. Again, I have to be careful to make it payable, right? And then what is the new price? The new price is the amount that the new king paid. But of course, before I change the king, I have to pay the previous king. So I just write king.transfer. So the previous king gets all the money in the current contract. So remember, we wrote that as address this balance. Okay, so this is like a very simplified version of King of the Ethereum, and I can now deploy it. So here's what's happening. Let's start with this one, with the account that ends in AB. It's going to deploy. Okay. Oh, by the way, I forgot. I want to also make this public, address payable, and it's public king, and let's say the price is also public. Okay, so I'm going to deploy. By the way, again, I have to say this many times in this course, even if these things are private, they're not actually private. Everyone sees everything that's happening on the blockchain. It's just whether other contracts can access it or not. Okay. So I have my function here. I can ask who's the king. This is the address of the king. I can ask what's the price. The price is currently 0. And now suppose that I use some other account. For example, I use the account with F2 to pay 7 Ether. And I call the depose function. And this was successful. I paid 7 Ether. So now king is this new one. The price is 7 Ether, 7 times 10 to the power of 18. And also, if you look at the balance of the previous king is paid 7 Ether. And of course, the current king spent 7 Ether, but a little bit more because, again, there are gas fees. Now, if someone else wants to become king, they have to pay more than 7 Ether. So let's say someone else comes along and they try to pay 5 Ether and call depose. As you see, this transaction failed. And because this transaction failed, because this require was failed, the transaction is reverted. So the only side effect is that the person who called this transaction paid for gas. But none of the other balances here actually changed. Okay. And by the way, the balance of my contract is always 0 because even though I'm paying the contract in this function depose, as soon as I'm paying it, it's transferring the money to the previous king. So my contract never really keeps any money, right? So let's say someone else comes and they want to pay 90 Ether to depose the king. So this is successful. They paid 90 Ether. They became king. The new price is 90 Ether. And you can see that the previous king was paid 90 Ether. Okay. Now, I know that, again, this is a stupid contract, but this is a real world contract that exists, and you can read about it here, and you can see that there are people who are paying actual money to become king of the Ether throne. And like the last person has paid 1.17 Ether. How much is that actually? 1.17 Ether. Yeah, so someone has paid 27,000 Hong Kong dollars to just be the king of the Ether throne. And yeah, that's it for the current session. I will put all of these links on Canvas. Please read these things, especially read the beige paper so that you can understand all of the details and also all of the jargon that we're using. Like, for example, we talk about vault state and all of those things. And yeah, we will write a lot of contracts in this course, but I have to just finish by saying that our focus in this course is not really Solidity. It's the kind of attacks and vulnerabilities that can happen with smart contracts. So we're going to use Solidity, and of course you have to learn to code in Solidity, but the same kind of issues happen no matter what other language you're using. So there are other programming languages for writing smart contracts. There's Viper, for example. And of course, if you're using blockchains other than Ethereum, they might have a completely different language. Some of the languages can be compiled to different bytecodes on different blockchains and so on. But again, that's the software engineering aspect of it. This course is really focused on the security aspect. So for this course, you just need to learn basics of Solidity, and you need to learn how to write secure code in Solidity.